toys right behind this wall. And this is Pete Harnish. Pete runs the undergraduate labs upstairs, and essentially we share the task of trying to make physics hardware a better way to understand physics ideas. And so every year we try to give some of the rest of the students in the area a chance to see some of this hardware. You may or may not have had the specific content that we're going to talk about today in class yet, but one of the things we can do here at Penn that you may not be able to do at your school is see some of these things happen. And so it's going to be very helpful, I think, to have seen it before you try to understand or read about it in your textbook. Okay, so if you haven't had it yet, try to remember what you're seeing, because I think it's going to be a real addition to any further efforts on your part to get this all to make sense. One of the other big things that happens here at Penn is that they do research. So this is not just an educational school. This is a school where scientists add to our knowledge of the way the rules of nature work. And some very important things have happened here, and it's worth having a little bit of a sense of where you are. You're at the intersection of 33rd and Walnut. Just a little bit down from the front door of David Rittenhouse Labs is this statue reminding us that Ben Franklin founded the school. It's one of the oldest universities in the United States. Okay, Ben came here, he was about your age, okay? So we expect wonders from 17-year-olds who come to this area. Did many things along with inventing the University of Pennsylvania. But currently, the location, you probably came in this door. This is David Rittenhouse Laboratory, named after the guy who kind of took the science baton from Ben Franklin. Okay, in the late 1700s, early 1800s, David Rittenhouse was the preeminent scientist in the United States. He did some very important work with astronomy, and he also did something quite interesting in that he is credited with inventing the diffraction grating, which is essentially a clear piece of material with very close together lines, something very much like a CD or a DVD. And you've all seen rainbows in CDs and DVDs. But David Rittenhouse was the first person to realize that this would be a very good substitute for a prism in breaking up light and seeing the color content. So the building's named after him. Directly across the street is a stodgy old brick building that you probably paid no attention to at all. That is the Moore School of Electrical Engineering. And in 1946, which is actually before I was born, but only by several minutes, Mauchly and Eckert put together 18,000 vacuum tubes and created the first digital computer. It was right there, okay? This was the beginning of the computer age across the street from here. It was not all that powerful, okay? Would have taken you the rest of your life to play Pong on it. It took $650 an hour of electricity, okay, somewhat more than a couple of button batteries. Took up the whole first floor of the building, cost $500,000, $1946, right? Today, $500,000 is like what? That's what the losers in the lottery are going to get. Okay, a 5 kilohertz processor, and we don't even talk about the memory in kilo or mega or giga. We talk about it as 20 10-digit numbers. It was essentially a really dumb Texas Instrument calculator, but it was the only one in the world at the time. Okay, so that happened right there. If we take a look catty corner from that building, we see the Laboratory for Research into the Structure of Matter. In 1975, these 3 Penn scientists, Alan McDermott, Alan Heeger, and Hideki Shirakawa, figured out how to combine what they knew about chemistry and physics to create electrically conducting plastics. Okay, you would kind of think of plastics as non-conductors and metals as conductors. But this was a very important breakthrough. They ended up getting the Nobel Prize in 2000 for that. It is not an accident that the Nobel Prize was 25 years after the work. Okay, the Nobel Prize is not given lightly, and there is, a fair amount of time taken to see if this is a discovery of any consequence. Okay, and so there was a Nobel Prize awarded for work in that building. If we come back over to this building, okay, in this building, a lot of interesting things have happened. Most recently, right here, along the first floor windows, is where our high energy department is. Our high energy department works on Fermilab, on the big atom smasher at Fermilab, and also at CERN. And several years back, if you were paying attention to science news, you know that the Higgs boson was very big in the news. All the images that you saw of the Higgs boson were made by apparatus designed and built by Penn. Okay, the Penn guys in that hallway over there are among the best people on the planet at figuring out how to detect elementary particles. And so Penn was very, very much involved in that work. And then, do we have one? Is there another slide? No, there's not. The other thing that happened here is that Raymond Davis started his work at Brookhaven National Lab on Long Island, but then came to Penn in the 70s and continued his work on neutrino astronomy. And he was the first guy to discover that it didn't seem like there were enough neutrinos coming out of the sun. And of course you'd say, who cares? The problem is that we're pretty sure there are fusion reactions at the center of the sun creating that energy, but it takes almost 1 million years for heat made in the middle of the sun to show up on the surface. So we only know what happened 1 million years ago at the center of the sun by looking at it. But neutrinos pass right through the sun. They aren't delayed like heat. And so neutrinos only take the same just about 8 minutes that light does. So if we can keep track of the neutrinos from the sun, we know what's happening in the sun right now. And so Ray Davis started doing that, and there were only 1/3 as many neutrinos as there should have been. And that said either that Ray Davis's experiment screwed up, the astronomers who thought they knew how the sun worked screwed up, or the particle physicists who told them how neutrinos and elementary particles work screwed up. It took a long time to figure that out, and finally in 2000, 2001, they discovered that the problem was we didn't know how neutrinos worked, that we actually had to change our understanding of how neutrinos work. And that is the kind of thing that leads to a Nobel Prize, a change in the fundamental laws of nature. And so Ray Davis won a Nobel Prize in what, 01, 02, something like that, okay? And so there's very real work going on here. There's work in many other areas. There's work in condensed matter. There's work in deep space, general relativity theory. And so the content of the textbooks is being added to by work that's done here. And so both those things are going on, and I think it's important to kind of have a sense of place here. Okay? So we are going to start at a whole lot lower level than that, because that's a kind of, science builds on knowledge, and we need to get the vocabulary before we can read the literature. Yeah, they're screwed in. This not happening. Oh, how about this? Yay! See, this is about sound and light. It's not about electricity. We don't know anything about electricity. Okay, so let's say that I were to give you a complex scientific task. And that is, I want you to ball up a piece of paper and hit these light bulbs. Okay? And so, everybody could grab a hunk of paper and ball it up. Now, inherent in that task is an assessment of where the light bulbs are, right? Now, if you were OCD, maybe you would pull out the 50-foot tape measure you carry with you at all times, okay? And tape it to your seat with the roll of duct tape you've got with you all the time, and walk down here and measure that, okay? And then go back to your seat having determined all of that, and now the tape is giving you a direction and a distance, and you can ball this paper up and throw it, okay? But that's probably not going to happen for most of you. Most of you are going to ball this paper up and kind of lob it. And some of you are going to get closer than others, but just about all the paper is going to land in a circle that's not much more than 10 feet around. Okay, so you're going to do pretty well. You're going to do a whole lot better than if I blindfold you and tell you to do the same thing. Then the paper's all over the front of the room. And so the question is, how do you do that? How do you just sit there and decide, okay, so for instance, the folks up in the front are going to decide, yeah, that's about 5 feet away, and the folks in the back are going to say, yeah, that's about 50 feet away, okay? And so we're going to propose that this has a lot to do with the light that's being emitted by these bulbs, okay? And so we've got some movie stars to help us out, okay? And we've chosen these movie stars carefully, okay? We can only use one-eyed movie stars, okay? So we're all set, right? Ooh, Mike, you know, people, you're fading, Mike. We need a sequel. The minions have taken over. Okay, so now if we put Mike out here and ask Mike to throw a ball of paper, okay? Mike's going to throw this ball of paper, and he's probably going to get direction right, but he's also probably going to not do anywhere near as well as you did on distance. Okay? So he can't see that. He's got the same problem with these light bulbs that you have with stars. When you look up into the night sky and see a bright star, you can say, yes, it's right there. But you can't tell me whether it's a big star way out or a small star up close. Okay? Because either of those things would lead to a medium bright star up in the sky. All right? So why do each of these guys have a problem? And why, if they work together, can they overcome it? And the answer, okay, so we're going to say they don't have depth perception, but what does that mean? What do you do to get depth perception? Okay, you take two images, and more importantly, quite simply, if you take a look at this, you know, we can put these guys vertically where you can kind of see the arrangement. They're not both looking in the same direction, but they're both seeing the same thing. And so they're going to kind of track along, and he's going to say, I'm looking at an angle of 30 degrees, and he's going to say, I'm looking at an angle of 0 degrees, and where do they come together? Aha. And you're doing that with your two eyes. It works for reasonably close things. Obviously, it doesn't work for stars. And the problem is, how big is that distance compared to how far is the separation? And so if we can spread things out further, we can triangulate over longer distance. And astronomers do that by connecting telescopes on opposite sides of the Earth. Okay, they can do that kind of work. So we can once again take that all on faith. One of the problems we've got with these light bulbs is that they're sending out an infinite number of light rays. It's not convenient for us to have you wander around the room to check on that, but as I walk around, the bulbs never disappear. So there's light going everywhere, and wherever I stand, I get a light ray running into me, and I can keep track of those bulbs. There are so many rays, in fact, that we have a very difficult time locating and assessing. And so, thank God for technology, just this year, the Star Shower Christmas decoration came out that lets you decorate your house for Christmas with almost no effort. That's right. All you have to do is take this baby, spike it in your lawn, and it even has a light sensor, which we, of course, have blinded because we want it to come on in the light. okay? And so it comes on when it's dark, and of course, if we want, ooh, we get two colors. We get red and green. It is so festive, okay? So this gadget's kind of doing what this is, but with a very subdivided group of rays, okay? Now, the other problem we have, and it's not a trivial one, virtually everything we study in science, we study by looking at. In other words, light becomes our tool. If I want to study a baseball, okay, I throw the baseball and I can photograph it, or I can, do a bunch of things with it, okay? But light is the way I see it. I run amok of trying to, what do I see light with? So for instance, I can shoot this laser beam across the room, and I can tell you that it started here and ended up there, and we can, ask you to believe that it travels in a straight line, but by now, you're no dummy. There are a lot of ways to get from here to there, and I could take a wiggly path, I could take a semicircular path, I could, there's a bunch of things. A straight path is one of the paths, but there's no evidence of what's going on. And so we need to find a way to see light. And the problem is we only see light if it hits our eyes. So the air is so clear that as the light goes through it, it just goes through it. But if we can put some particles in the air, we can grab some of the light that would have hit the wall, let it hit a particle, bounce off the particle, go out in the room, and where you see a lit particle, you can pretty well assume, light was traveling in that zone. And so how do we do that? And so now we've got some fairly decent evidence that light indeed travels as we have asked you to believe. Okay? Wow. And so that laser is looking pretty straight. Oh boy. And our beams here are looking pretty straight. And now, if we bring in our minions, okay, it's pretty clear what they would be seeing. And we can get a little more. I know the demo's not working if I can breathe. So now these guys can narrow in on just like a Bowie concert in the 70s. So we then get this spreading of beams. If we come back to the light bulb, we can see it's pretty hard to see that event because we filled space with the rays. It's much more helpful if we can see the rays without overlap. If we turn this around, sometimes you can see it somewhat better. Yo! That's pretty cool stuff.
It's like a diamond.
If you're along the line, now this is a glycerin-based smoke, so in fact it's the same stuff that's probably in the cough medicine you'll take. Right. All right, so the other thing that's interesting is that if we go back to geometry, where Euclid was busy having postulates, we have a pretty good sense that the postulate of straight lines and things like that, in fact, were based on evidence. Okay, if we just watch sunlight come through, gaps in the leaves in a forest, we see straight lines like this. So the idea of straight lines is probably based on physical observation, okay, applied to those situations. Okay, so when we say we see something in a location, then we are essentially suggesting apologies here.
Oh my God.
So now we turn up a light. So let's take this. So we've just addressed this interesting question of what does it mean when I say, give me what? So if I ask you now to throw a ball of paper, not at the light bulb, but at the bulb you see in the mirror. Okay? So now we've got a really interesting problem. Okay, where do you throw? Does the mirror give me a bulb that's the same as if I simply took a photograph of the bulb and made a print of it, right? So I have a little poster of a bulb, in which case you would say it's right here, okay? Or do we see it at some other spot? Now, as a quick indicator of what might be the case, can we blow up a little smoke? Show this here happening. So if we take our light here, can we do anything? Can we block out the door? So now we've got, all right, the light is coming up, it's hitting this mirror, and it's scattering up to the ceiling. But if I've got Mike and the minion, yeah, okay, give me a really, yay. Okay. So now you can see that this stuff is coming up here, going up to the ceiling, but notice that it is scattering. Imagine that we've got Mike and the minion here, okay? And they're going to go up here and they're going to say, well, I see it all coming. Is it at the mirror? No, it's back here. And so the mirror is making it look like there's a light source not on the surface, but somewhere back there, right? And that's what we'd like to investigate next. So we've got a really interesting mirror here. Okay, this is a piece of pink plexiglass, and we can put an object on here. You can see we spared no expense. It's an old vinegar bar. Okay, so we can put that right there. And if we take the lights down a smidge, okay, it's not too hard to see a reflection of that bottle, okay, in the mirror. So the question is, where is that reflection? We've used this mirror on purpose because it's transparent. And so we can actually put a guy behind you. So now you can see both of these. And in fact, you can tell which is which because the one that's pink is behind it, right? Because you're seeing transmitted light from behind, and it gets colored, and then you're seeing reflected light from in front, and it retains its color. And so the question is, can I get these guys to fit together? And so when I do that, you only see one object, okay? And so they are sitting in such a way that the reflection of the front guy is visually in the same place as the rear guy, okay? Are we seeing that? Is that good? And consequently, our report of where is that light is that it looks to be behind it, okay? Now, Once again, too many people to get everybody down here to see, but we can solve that. I think. And see if there's any down. Check out how little hair I have on my head. Okay? But now we're looking straight down on this, okay? And we can see what we've done. So you can look here and see the effect, okay? Here's the mirror, here's a meter stick, here's the 50 centimeter mark, and we've got 10, 25 centimeters, okay, gets me to this light bulb, and we've got 10, 25 centimeters gets me there. So in other words, the image that we see here is looking exactly like a bottle that is the same distance back as the object is in front. Okay? And so you can see this from the side as well. All right? But the overhead view, I think, is worth having. All right? And so, what does that mean? It means that if the light rays are scattering from the object, when they hit the mirror, they continue to scatter. And we have now been somewhat fooled by the fact that we grew up thinking light traveled in straight lines. The mirror interrupts that straight line. But we still act that way. If we see diverging light rays, we assume the straight line and we just keep tracking back to where the converging point would have been. We call this a virtual image. Can we be fooled by that? We know that birds are fooled by it. They fly into windows all the time. Okay? And occasionally we know deer try to run through plate glass windows. But you're way too smart for that, right? Okay? There's no way we could fool you, right? Right. So this delay is because I knew damn well that I could not leave it out and keep your attention. Because we have the most transfixing object on the planet right here. Okay? That's right. Regardless of how cool the physics equipment I can bring out is, you will look at a mirror rather than anything else. Okay? There's nothing I can distract you. And so, and you know, swing it over here. Let these people take a look at. Oh my God, I should have not come out wearing that. So we've got this mirror here. You're looking in the mirror, and you're seeing what Lewis Carroll talked about as through the looking glass. There is a second class of really good-looking students right back there. How far back? Well, in fact, they're sitting exactly as far behind the mirror as you are in front of them. Okay? But now, we were talking, you know, are you fooled? Do you believe that we've discovered your long-lost twin? Okay, and brought them all here? Is this an Oprah show? Okay. Probably not. Okay. So how do we fool you? So we purposely set this up so that I can do this comfortably, right? You know, this is the second approximation. The first time we had it sitting upright and it was really uncomfortable. Okay, so you put it down so that it wasn't that high. Okay, so now you can't see my left leg, except it doesn't, you know, it kind of looks like you can see my left leg, okay? Because, right, we're going to venture into the dark science of biology and talk about the fact that I am bilaterally symmetric. And bilateral symmetry, if you go to biology class, they will brandish physics words without a license and tell you that the left side of your body is the mirror image of your right side. Okay? So my left leg looks just like the mirror image of my right leg. Son of a gun. There's the mirror image of my right leg. It looks like I'm standing on 2 feet. Okay? And so all of this works. Years ago, they used to talk about lifting yourself up by your bootstraps, which of course is the metaphor that led to booting your computer, that it's going to start itself. Okay? And lifting yourself up by your bootstraps references a world where boots didn't have zippers, where men were men and women were women, and boots were brutal to put on because they didn't, you know, your foot didn't want to bend at that angle. Okay? And so there were straps at the top, okay? And you pulled like crazy to get these things on, all right? And so it was thought that maybe, you know, once I have my boots on and I'm standing there, I can grab those straps and pull just as hard and pull so hard that I lift myself off the ground. And along came Isaac Newton and disavowed people of that idea. Okay? The third law seemed to interfere. However, maybe we can change that, okay? Because now we've got you believing that you're looking at both my feet, okay? And if we do that, and I try to pull myself up, and this is really a hard thing to do, okay? I don't recommend doing this at home, okay? Because it's tough to balance once you're up in the air. But if you pull, and remember, you got to lift your whole weight, right? And so now, we've really got an illusion, right? So we've been talking about physics up till now. We've been saying that the image appears behind the mirror, but now you're looking at a situation that's completely silly, okay? And without physics, you know, I could claim that I had superpowers or all sorts of things. I could claim, for instance, that I could solve 76 problems that I could. Okay? But in fact, it's nothing of its sort. And I should point out that I've also had to practice this because when we first started, I actually had my feet spread, and I can't stand over the mirror with my support leg way behind the mirror. So you've actually got to get your foot right up against the mirror so that your center of gravity is still directly above your support when you lift this up. So you kind of have to work on that. But this is what we mean. This is a virtual image. Okay? It's virtual because any attempt to reach that left leg is going to be interfered with by the glass. Okay? And more importantly, if you try to do the Lewis Carroll trick of let's go around the mirror and get to the other side, it ain't there. Okay? So this is used in many ways. Okay? One of the standard uses of a plane mirror that acts this way is to produce visual space in a small room. That if we put a big mirror on one wall, the room looks a lot bigger. Okay? Even though it's not. You really can't store that stuff you have nowhere to put on the other side of the mirror. But at least it feels good. Okay, so we've got a virtual image there. And yeah.
So far we've been talking about flat mirrors, right? So flat mirrors get a little bit goofier when you're not at them, right? When we were doing a lot of this stuff, we had to angle it around so that everyone could see. So as a quick demonstration, thank you. Tell me when you see yourself right in this mirror. Right? That pretty good? All right. Who do you see in this mirror? You. Who do you see in this mirror? All right. You. Who do you see in this mirror? All right. Someone over there, right? But this mirror only works if it's aimed directly at you, right? Because it's going to reflect right off it. Now, this gets a little bit more interesting if we had two mirrors, right? Because if I had a mirror that was aimed at you, you could see you. If I had a mirror that was named U, you could see U. Right? So if we take 3 mirrors and put them together, who do you see in the middle of this mirror?
I see the man behind me.
So this is called a retroreflector. Right? So by the geometry of these 2 mirrors, it's just 3 mirrors at a right angle, right? It's in the middle of a milk crate, right? That as long as you're in front of this mirror, no matter what direction the light comes at it, it will bounce enough in here that it will come back to its source, right? So if you've ever played catch against a wall, right, that ball can kind of go all over the place. If you play catch against a corner, it could bounce 3 times in the corner, but it will end up coming back to you. Now, what's extra interesting is that one of the great evidences that we have gone to the moon, despite what some lunatics think we haven't, is the fact that we have trailers full of those on the moon, so that we can shoot a laser at them from an observatory, and will bounce around and come back, right? So this is not that great because we built this one. Right? Up there in that back corner, right, you see there's a little black circle there. That is an optical grade retroreflector. So if I can hit it, all right. Yeah, I know, my hand is a little bit shaky. I've had a lot of coffee today, right? But what's interesting is that anywhere in this room, if I can hit that, the laser will come back to me here, right? So that's 3 meters. If we start going to even more than 3 meters, we can start to get some particularly goofy things, right? So if we have 3 mirrors, you can imagine if we had 6 mirrors, we can make it even more interesting shape. If we had 1,000 mirrors, if we had 10,000 mirrors, if we had infinite number of mirrors, we could make ridiculous things. Luckily, I happen to have an infinite number of mirrors here, right? So this is a sheet of Mylar. So normally it looks like 1 mirror, but very quickly I can make it an infinite number of mirrors that are all pointed at slightly different places, all right? So it's a little hard for me to shine this like at you guys so you can see exactly what's going on. So we'll do it this way, so you guys can see. All right, so you see that? Right, so this is effectively a funhouse mirror, right? Now, you guys will notice that there's a place where I can bend them, and all of them start lining up on top of each other. Right? That is a very specific shape. Right? I do not have the ability. You can imagine if I have one bent that way and another bent the other way, then I can also get them down to a point, which is beyond my abilities to bend things. Luckily, they happen to make mirrors that are that shape, which is this guy, right? So if you just look at it for a second, it looks a little bit funny, right? Especially, it's going to look funny, different to you guys because of where it is. But if you want to bog fire me a little bit.
Okay.
What on the back?
The jump for the telegram? Oh, I mean, a hologram. Alright.
Okay. So now we can see these a little bit. Now, what's particularly interesting here is we've already established that this is a point source of light. We have light coming out, it's spreading out, right? When we hit a flat mirror, it changed directions, but it kept spreading out, right? We still had that chunk of cone, it was just moving in new directions. But if we look about here, all right, if we can get it a little bit sideways. Actually, if you could bog fog me a bit more.
And you want it up?
If you could bog it. All right, so we have a point source. They all come in here, and then they come back here. Right? So they come back together. So now we have into a point, and then they all hit this, and then I'll get focused back into a point. Now what's particularly interesting here, as I move closer and further away from that point, from the point source, we can see the point in space where they come back together is moving, right? But if we get close enough, they don't come back together anymore. Right? They're actually now perfectly, if I get this just right, I can make them all perfectly straight. Any ideas why this is? Right, so it's concave, right? So before I had 2 points, right? There's always going to be 2 points. The point where everything was coming from, and the point where everything was focused to. Where is the singular point where all of these beams meet? Right? No, not on the wall, because you can see that they're all flat like that, right? If you follow these lines, where could you go where they meet? Where could you go in that way, where they meet?
Through the wall.
Through the wall? Yeah. How much through the wall? Infinitely, yeah. If I got this perfectly parallel, we could say that it is focused infinitely far away. Right? Yeah, it is very Death Star. Now, the interesting thing is, this also works backwards, right? If we had, that light is just working in straight lines. So if we had lights out there aiming here, they would still come in to a singular point here. Now, besides the Death Star and Captain America's shield, is there anything else that this mirror kind of looks like? Sphere, sun, especially this, where you can kind of imagine like a big kind of can that's held in space in front of it, and then it's like up on a roof.
A radar dish?
A radar dish, right? A satellite dish, right? Any form of satellite dish. That's how this works, right? That if you have any source out there and it's coming in, it will all be focused onto that singular point, right? That's why we make radar dishes this shape, because they can focus everything down to a point, which then we can have our small sensor right at that point instead of making a sensor that is this big to pick up all of that light. Right? When we build satellite dishes, this is what we do. We also do this, you can also do this for sound, if you've ever heard of a parabolic reflector. Right? That any kind of wave would work in this. So this also works. It's a little hard to demonstrate for this size. But if I put my ear at that distance away from this, and I line this up correctly, I should be able to hear any sound any of you make in this room. Because the sounds would bounce off this and go directly to my ear. So it's effectively an ear that is this big. Right? There's all kinds of fun stuff we can do because of the math of this shape, right? And it is a parabola, right? Which you guys may remember from math classes, right? So it's just a feature of that geometry, despite whatever kind of thing we have bouncing in it. Now, to talk slightly more about this, we're going to switch over to this guy. Because here, we had a uniform source of light, right? That it's a cone coming out in space. And if I told you that that was the top of the light or the bottom of the light, if I numbered each of those little green dots, they would all look about the same. So instead, we're going to do it with a light bulb. So provided that we did not get this card. Yeah. Take a look in the mirror. So looking into the mirror, how many light bulbs do you see? If I did this right, you should see two. Right? But as I put it sideways, you can clearly see that there's only one. So let me switch to my camera here. If I switch to my camera, I can get everyone into kind of an optimal scene. And there. So, looking at the mirror in the screen, you can clearly see two light bulbs, right? Except that light bulb is not there. Now, you could set up a mirror, right, so that you can see this. But as we shown before, where you are compared to the mirror is really important. But as long as I stay within kind of the scope of this mirror, it's going to stay lined up. And to doubly prove my point, as opposed to doing with this, we can now go back to ray tracing for a moment, but very specific ray tracing. That if I put a piece of paper here, we can kind of see the image of that light bulb projected onto the paper. But if I use a laser pointer, I can trace out that light bulb. Now, what's really great about this is as I move my laser, right, you can see I'm wiggling my laser quite a bit back and forth here, just sideways. And it's really not changing at all on point. If you guys see, some of you guys can kind of see here on the mirror, from this particular point, I can scan my laser all the way across the mirror, and it doesn't really move on the page. Because how the light got from this bulb to this paper is not important on this mirror. Just where it started. And as long as it starts at the same place, it'll end on the same place. So, this has been bouncing light. Right? We've had straight lines, and then we've changed the direction that those straight lines are going based on by bouncing those straight lines off of objects. The other way that you can choose the path of a straight line is by bending the path of the line. So if you give us just a second to clear off some space here, we will bring out a couple of new toys so that we can explore bending instead.
Is this what college language is? Like, would it be this way?
All right, so Pete's been talking about changing light path by bouncing. And I hope we've established that the idea of changed light path leads us to images, to visual appearances that don't correspond to physical objects, okay? And you almost could liken that to the adolescent behavior of burning your friends, right? You're walking down the hallway, and you reach around behind their back and tap them on the other shoulder, and they look away. Everybody laughs because they've been fooled, okay? But in fact, they are demonstrating that they are good scientists. The assumption is that cause and effect are connected, okay? And so this is what happens when we form images. We've got light coming from a place where there's apparently no source, okay? And we end up with images. But we can also do this by bending light, okay? So rather than having it hit a flat barrier and change direction, okay, we can do this with transparent materials. Thank you. So what we've got here is a semicircular dish, or a full circular dish, that's half filled with water. So it's even marked off like a protractor. There's a beam of light up top, it's shining down, and right at the diameter line, okay, is a change from air to water. And you can see the light is passing through. And this light kind of works, but there's another way. You know, we took this laser pointer and stole the gadget off of a laser level and put it on there. And so instead of a dot, we've smeared this laser light out into a horizontal line. It's a sheet of light. If we had smoke in the room, okay, you would see this as like a flat surface. But now the neat thing is that unlike a normal laser pointer that I can hit the ceiling with and you can't see, I can do this and you can say, wow, that's a straight line, okay? And so this lets us track this maybe even better than the old original apparatus. And so if I take this guy and shine it down there, we can see that that light beam is going through. And let's see what else. Okay? And so it's going straight through. All right? But the interesting point is, if I don't hit at right angles, now we're seeing that that light kinks as it crosses. And so that's no longer a straight line path. All right? It's coming in at a 20-degree angle and going out at about a 45-degree angle. Okay? Yeah. Right. And so we end up with a very visible bend in that light path. This is called refraction. Okay? And probably the most famous of the refraction devices is a prism. So this is a case where we're just changing one light path. But if we, and you know what we need like medium light. Okay, so I've got a fossil of a device. Just so you can see this whole thing. Okay, so this is a carousel projector. Used to use slides, okay, before the days of digital anything. And we're firing this light beam across the tabletop. We have a couple of prisms, triangular shaped glass doodads. And if we take this prism and insert it here, we can see that the light is really changing path, okay? But another really interesting thing is it's also changing character. So what started out as a white light beam is now ending up as a rainbow light beam. Okay? So we've got, you know, our old friend Roy G. Biv, okay, sitting here. This was a much discussed phenomenon in the Renaissance Enlightenment period. And one of the reasons that people thought that crystal chandeliers and gemstones created rainbows was that there were impurities in them that colored the light. And the person who came along to dispute that thought was Isaac Newton. And Isaac Newton said, no, what's happening is white light is not pure. The assumption was that white light was pure and that we were messing white light up with the prism. Newton said white light is a composite. And what we've got here is color. Now, you know, this could just be a he said, she said argument if we left it at that. But this is the point, and this is where Newton and Galileo and the early guys in science kind of defined a new way of knowing things. Because rather than debate the point, Newton said, well, look, if you're right and we put another prism in there, we ought to get more color. But if I'm right and I put another prism in there in the right place, I can bend everything back. And I can make white light out of the colors, because I'm telling you that the colors, okay, were why I had white light in the first place. And so if we look at this carefully, we see the light beam coming in such a way that the flat base of the mirror is here, and the light bends away from the point toward the flat base. We're also noticing that in that bend, red light is bending the least, and blue light is bending the most, and the other colors are in between. Okay? So what we'd like to do now is get this light and get it to bend the other way. So we notice that light bends away from the point and toward the flat sides, right? And if you can't remember how to do that, you just go out and you get your old Pink Floyd album, okay? And on the front cover of Dark Side of the Moon, we've got that picture, okay? This is a really cheap t-shirt, and they didn't put the backside of the album, but Pink Floyd did. And Pink Floyd did the other half of the Newton experiment, okay? Which is what we're about to do. So we're going to bring this guy in, okay, and grab that light. And if we put this thing here, lo and behold, we're back to having white light. Okay? And so we took the colored light there, we reassembled it into white light. And this is a really big step. This once again is an evidence-based statement that, all right, you guys who thought that this was because of impurities in the glass can't do this experiment. Okay? This simply does not work in your theory, whereas, you know, in what I'm proposing, I've got a really good explanation. I overbent the blue light here, and then I overbent the red light and put it all back together. Okay? And we end up back where we started with white light. Okay? So that's a very important point. And now, do we have an image worth seeing with that?
Yeah.
Okay, and so we've got our lasers there. The problem with these cameras is that the light intensities really confuse the color sensors in the cameras. So we can see the light paths, but we don't really see the colors terribly well. The other point worth noting is that one of the things that happens with diagrams, okay, Pink Floyd did not include all the light here. So for instance, if we look over here, right, we've got the bent light going that way, and then there's a beam that doesn't show up on my t-shirt. Okay, what is that beam? What's going on there?
Reflected off the prism.
Okay, it's reflecting off the prism. Okay, so shiny surfaces, even without silver, okay, can reflect. And so we've got a reflected beam coming off the back, which is not being refracted, right? It's being reflected. And so if we're diagramming refraction, oftentimes we leave it out. Somebody comes along, tries the experiment, and says, what's going on here? Okay, and maybe we've oversimplified. Okay, so what's happening? Can we make any sense of this? So, we're going to make sense of this, if that's even possible. So we've got some big floppy shag rugs we're going to put on the floor, and you say you can't see anything, but we're going to turn on that horrible camera that shows my bald head, and then you're going to be able to see it, okay? And we've got a light ray. Well, kind of. So what do you mean a light ray? All right, imagine that you are now microscopic, and my laser pointer here is huge, and the beam coming out of it is as wide as this, okay? And here's the light wave coming at you, and it's going to hit you and knock you for a loop, okay? So here's my light wave. Now, I am going to send my light wave, where am I? Okay, I'm right there, all right? Let's move this guy a little bit, all right? So here's my light wave, and it's going to arrive and enter at right angles. Remember, here we had this guy comes through and just goes straight. So here I've got floor, here I've got carpet, okay? And for the most part, we cross straight. What's wrong with this wheel? Okay? And there's not much change. But what if I come in at an angle? Okay? So now let's see, if I come in here, we see a rotation. Oh, really turned there. And there's a very clear change in direction. So in other words, it's now headed that way, and I sent it in that way. Okay? Why did it change direction? What happened there? And slowed down, exactly. If I enter this thing in such a way that one side, because the carpet is harder to roll on than the floor. So if I arrive like this, everybody slows down and we cross uniformly. But if I come in like this, one side slows down, he doesn't slow down. And so this thing turns, okay? And I'm sure you all knew that from driving bulldozers, right?
Yep.
Right, what else would you do with your free time, okay? I hope that you have wondered how a bulldozer turns, right? Isn't that a conundrum? There's no steering wheel. It's just these two treads and they go along, right? And what do you do to make it change direction? Slow down one side, okay? You know, what about the one-armed guy rowing a boat? Right? He doesn't need a very big lake, does he? Okay? Because he's got one side's fast and one side's not moving. Okay? So we've established the fact that a speed change can cause a direction change, and that is refraction of light. But there's another interesting principle. It's a sophisticated principle, so we need some of the most complicated equipment we own, which is Ken and Barbie. He may still be. So we've got Barbie in the lifeguard stand, and we've got Ken out swimming. Okay. So now please notice, we're in the same reference frame. So Barbie's in the lifeguard stand on the floor where you move fast, because you can run fast on the beach, right? Meanwhile, Ken's out swimming in the ocean, and nobody swims as fast as they run, right? So this is the slow area, this is the fast area. Everything's peachy until dun, dun, dun. Yes. Okay, so now Ken's got a problem. He needs a lifeguard. Barbie, of course, did not sleep through math class. And so she knows that the shortest path between 2 points is a straight line. But then she starts having inklings of her physics class. She says, oh my goodness, I don't go the same speed on the beach and in the ocean. So maybe I should try to minimize my ocean trip. So what if I run across the beach until I get to this spot so I can go into the water at right angles and have the shortest possible time that I spend swimming slowly, okay? Which means that I want to run from my lifeguard stand over to that point. So now we've got, and see, luckily we've got a device called a 2-meter stick. That's a 2-meter stick, and we've got devices called meter sticks. So here are 2 meter sticks, and here's a 2-meter stick, and here's a big gap. And this big gap is screaming loudly that this trip is longer by a non-trivial amount than this trip. In fact, it's so much longer that the time you save by not swimming very much isn't enough to make up for the time you need to run this far. So this is not a quicker trip. But this is a good idea. And the good idea is, all right, let's not get this extreme. Let's not make the trip so terribly long. But let's set it up so we reduce the swimming and increase the running. And there will be a point here where this works. Okay? And that point is the point at which the sine of the angle of incidence divided by the sine of the angle of refraction is equal to the ratio of the 2 speeds. You think Ken's in trouble?
And all the time she's
It's Barbie. Barbie can do this. Come on. Come on, it's the 21st century. Women can do anything. You should remember she was a doctor. Ken is dead, huh? And it's about time. So the index of refraction, what I'm driving at here, though, is a really interesting point. And that is what we call the principle of least time. And that light, one of the underlying principles of light's behavior is that it always takes the path that it can cover in the least amount of time. And our rule about reflection, angle of incidence equals angle of reflection, can be shown to be the shortest time it takes. If we've got point A, point B in a mirror, and the angle comes in and bounces, that path is the shortest path you can take in time that lets you touch the 2 end points and the line of the mirror. Okay, and it's a neat calculus problem, because I know you're looking for neat calculus problems. Okay. All right, and what do we get? And we've got time. Okay, so one of the cornerstones of scientific theories. Like how do I do a good scientific theory? Well, I take some observations and I assemble an explanation that takes care of it. And that happens a lot. But it turns out that there are many explanations, and there's kind of a gold standard for a scientific theory. And that gold standard is, okay, I've seen something, I've explained it, okay, nice. Can I predict with it? Now that I have this new idea, is it good enough that it will suggest to me something that I had no idea would have happened up to that point in time. And if I can go from explanation to prediction, then I probably have the attention of the scientific community. It's not a lead pipe cinch that I've got, you know, a theory that's going to last, but it's a whole lot better than if I couldn't predict something new. So what we have suggested is that we now understand what goes on with refraction. So let's say that Santa was particularly good to you, and you decide that you are actually going to be a cooperative member of your family, and you say, Mom, I'll do the dishes. Okay? Right. No, Santa wasn't that good, right? So you go into the kitchen, and there in the sink, okay, you've got water, you've got a glass in the sink, okay, you can reach in, and you know exactly when your hand is going to get wet. You know exactly when your hand is going to grab the glass. You can pick it up. And the question is, how can you do that? You've got all kinds of clear stuff here, right? You've got clear air, you've got clear water, you've got clear glass, and we even have a clear sink. And so why is it, you know, it would be easy to answer this question if this were a pot, right? If it were opaque, and we could just say, yeah, well, that's where the light's bouncing. So what's happening here? How do I know where that is? Go further.
The light bounces back at a different angle or speed.
Okay, which leads me to what? What's my observation? I'm not sitting here with a speedometer.
You can see something quicker than the other one.
It isn't quicker. Different. Okay? So the fact that the light is changing speed, and remember, it changes at the boundary. Once it's through the boundary, it doesn't change anymore, right? But at the boundary, if it changes speed, it changes direction, and we get a distortion. And so the presence of the glass and the water creates, there's clear water, no distortions. We're not ready to believe there's anything in there. Okay? So here's the glass, and what we're saying then is that the glass has a different index of refraction, which is another way of saying it's got a different speed of light than air or than water. Okay? So we actually have three. So let's imagine, what would it be like if the speeds were the same? Would it really disappear? Is there any chance it would disappear? So what do you think? Does this guy disappear? He's not. Is this glop? This glop is proof that I am really interested in having this show work, because when it's over, I have to clean up 5 gallons of corn oil. This just sucks. But it's a good demo. It's a great demo. So I could fry stuff, yeah. I could, you know, get biodiesel in my car. I could do lots of stuff, right? So what we have here is a plastic graduate, and it's kind of still visible, okay? And here we've got a Pyrex beaker, and that's why we're using corn oil. And we could put that in here, and it's a little harder to see than that. It's not as hard to see as we'd like, but let me tell you that we now have 2 beakers in the water. Not the water, the corn oil. Okay, and you say, what do you mean we have 2 beakers? And Pete's gonna get messy. There's the other beaker. Okay, now part of the issue is that the index of refraction of corn oil and Pyrex is around 1.46. And that means that the speed of light in a vacuum is 1.46 times faster than it is in Pyrex or corn oil. And I suppose we should give Pyrex its due. This is the 100th anniversary of the invention of Pyrex. And if you get to your cooking store, you can get your anniversary Pyrex dish. Okay? What is Pyrex? It is borosilicate glass. It's glass with a formulation that doesn't expand or contract much with heat. So it doesn't crack when you heat it. Okay? So it's got a slightly different index. We can't do this with regular glass. We could match perfectly in the old days when we didn't care about cancer. But now we just have this wimpy, namby-pamby world that worries about dying of cancer. But back when we didn't care, we could mix benzene and carbon tetrafluoride, or tetrafluoride, and come up with an index that perfectly matched glass. And it really did disappear, okay, just a little bit before the physics teacher did. Okay? So, corn oil is a little more, a durable example that we can use year after year. Okay? And so if the index of refraction doesn't change, even if we've got solids and liquids, okay, things don't, the light doesn't change path, there's no distortion, and the beaker pretty much disappears. All right, I think we're done. Now, we've got some refreshments out back. I don't know quite how many, don't take more than, don't dive in and take 3 or 4. Okay, there are drinks and pretzels. We said restrooms, men's rooms down that way, ladies' rooms down that way. I'd like you back in 10 minutes because I've got an hour's worth of stuff to do in 40 minutes. Okay? Remember my soda? Yeah. Good. Perfect. So, we know that the car traveled because we deliver energy, okay? And our sensor, regardless of what it is, okay, reports that energy. There's another way to deliver energy. And this is one of the reasons it was worth taking a bus trip, because this is something that so now I can deliver energy like this. And we just heard that energy arrived at the end because it hit the cup. Okay, let's try that again. Okay, so we can make the same noise, but we've got a really different process. And one of the important things is, if I, one of the examples I used to use in class, I taught high school for 25 years. And I would say to students, okay, particles, if you fall asleep, I'm going to try to wake you up by throwing erasers at you. And of course, if you're in a physics class, you're probably not a dumb person. And so, most of my students would look at the front of the room and say, oh, he's got 4 erasers. So if I'm the 5th guy to fall asleep, I'm in good shape. Okay? He's out of, he can't deliver energy. And so once that happens, I say to myself, well, all right, why don't I, so 2 weeks after I've failed abysmally, you come back on a Monday morning, and I've got clothesline running down each aisle, tied to eye bolts in the back of the room. And now when somebody falls asleep, I pick up the clothesline and I just whip it. Okay? And we send a ripple down there, and everybody who's awake dodges it, and the one sleeping person gets whacked on the head. Okay? But the point is, I don't run out of clothesline. Okay? At the heart of this is the difference between a wave and a particle. I can keep sending energy, and I don't ever lose stuff. Okay? Now, this is a complicated behavior. We can probably, what we'd like you to do is to just see this motion. And one of the things that you do in a physics lab is you have equipment that lets you focus on the variables you want to study and eliminate the other ones. So there's a lot of junk on this table, and we can make it go away by turning the lights off and lighting up these dots. And so now we can really take a look at our waves, and we can say, well, here, let's send a pulse down. Okay, and then that pulse comes back. All right? So if we turn the lights on for a minute, let's take a look at this experiment with particles. So I'm going to send a particle down, and here it comes back, and so particles really have a bad job coexisting. Okay, they run together. And so we end up with a collision here. Okay, and in essence, I can keep, this guy would go down here, reflect at the end, and come all the way back. And waves will do that too. So that guy goes down and comes all the way back. So what we just discovered, though, is that I can keep this particle from coming all the way back by doing that. So can I do that with waves? Okay, so if we turn the lights off, pump this guy up. Okay, and so here goes a wave. And he's going to reflect, and here goes when I'm going to stop him, and no, I didn't stop him. They pass right through one another. Okay? And they do something else very interesting. When they collide, let's say I've got a 2-inch wave, well, 4-inch wave, and a 4-inch wave, and boom! Right in the middle, we get a really high one. They add up. Okay? Let's do something else really interesting. Let's send a negative wave and a positive wave, and right where they cross, they actually, the plus and the minus cancel. Let's try that again. Negative pulse, positive pulse, and of course I've got to get them to be equal. But the critical point that we've illustrated, I can get lights in this thing. This is called the principle of superposition. And this is probably the biggest single distinction between waves and particles. Okay, particles run into each other and stop. Waves pass through each other. The light coming down from the ceiling is not interfering with the light coming in from the front of the room. Sound directed from the front of the room does not interfere with you saying to the person next to you, wow, this guy is really good. And so you're allowed to say that at any time. Okay? So we've got waves of that type. This is what we call a transverse wave. It's a wave in which the medium, which is the stuff that's wiggling, moves at right angles to the direction the energy is traveling. So the energy is going from left to right. The lumps of stuff are going up and down. Okay? This is the kind of wave we see with light. It's the kind of wave you see in the ocean. Sound, on the other hand, happens because air is a gas. I can't push a gas sideways and have the air next to it care, right? Like I grab this air, and this air just doesn't give a damn, okay? But if I've got a spring in here, when this spring gets pulled up, it twists and moves this next guy, and twists and moves this, okay? And so I need kind of a springy connection. And it's critically important. I think one of the best things to do when you're studying something is to say, all right, what's the controlling factor and what if I change it? Why does this wave happen? Can I go back to my school? Like, this looks like a mess. Like, you'd need like a machine shop with 12 machinists and a big budget. And couldn't I just get a hunk of plywood that's like the same width and wiggle it? Well, here's the hunk of plywood and I wiggle it, and that's pretty dull, isn't it? It's not as cool as this. Right? Now, why isn't it as cool as that? It's not as cool as that because it's rigid. Because we don't have that springy connection between adjacent parts. Okay? And so air doesn't have a springy connection in shear, which is to say sideways force. It does have a springy connection in pressure, which of course is why you can dribble a basketball. Okay, right? The ball hits the ground and the air smushes and then it springs back and the ball pops up. Okay? And so we can have a push-pull wave in air. That's called a longitudinal wave. Okay? With no spring at all, we get nothing. And of course, if this were a meter stick that I pushed, the whole meter stick would move at once. But this delay, which is critical to the behavior of a wave, is a delay that's induced by the inertia of the stuff and the springiness of the connection. And so if we take the lights out for a minute, again, this is a complicated mess. Let's get rid of the complications and just see the domino effect. Okay? And when I send out sound waves, I've got air molecules pushing and pulling. Okay? And we're going to be doing that to a greater extent in a minute. And so here we've got an illustration of what we mean when we say we think something is a wave, and we have some suggestions of tests. Because critical to a scientific statement, when somebody says, is that a scientific statement? Okay, most people think, was it made by a guy in a white coat? And that's not the case. Okay, a scientific statement is a testable statement. There has to be something you can do that lets you say that was right or that was wrong. If it's not a testable statement, it's not scientific. Okay? And so, for instance, saying that I like vanilla ice cream is not a scientific statement. It's not testable. Okay, we have to believe that. All right? Okay, but the world will end tomorrow. Sounds ridiculous, right? But that's a really scientific statement. We've got a great test coming. Okay? And by tomorrow, you're going to be able to tell whether that was a good statement. Okay? And so that's an important thing to understand. All right? So we'll give this to Pete, and
so here we have a bell in a jar, which happens to be a bell jar as well, which is nice.
but kind of different.
So if I turn this guy on, and we're quiet, we can hear the bell. If we look at the video, we can also see the arm moving that is hitting the bell. Right? So we have, with our ears and with our eyes, we can verify this is happening. So the sound wave is being produced by this bell and is getting to you via a wave, as we said. So what is the medium that the sound wave is getting to you? Right? Air, right? That it's moving air, that air is moving you. We have this light. The light is a wave, as we've mentioned, and it's getting to you. What is the medium that it is waving through to get to you? You guys can just yell, it's fine. Right, air, cool. So, the sun is a light source that is producing light. What is the medium that the sun's light is waving through to get to you? Air, sure. Then there are another 93 million miles between the air and the sun. So what medium is that going through? That is actually going through space-time and stuff, which is way above what we're going to talk about. The point is that light can go through a vacuum. I have said this. I work here, therefore it is a scientific statement. Not really, right? We can say that it's a vacuum from here to the sun, and that the light can get there, but we couldn't be able to hear the sun. But you kind of have to trust me that it's a vacuum out there. So, to test that, we can isolate these two phenomena. So, this jar is also next to a pump. So, I'm going to get this bell ringing, and then we're going to pump all the air out of it. So, it's in a vacuum, and we can see what happens. Now, here's the thing to notice. So as we watch the video, right, we can see it's all moving, right? We can still see it producing. One interesting thing to notice, look at the spark up there at the top. The spark is getting bigger and bigger and bigger. Some of you guys up here might be able to see the spark just with your eyes now. That is because the spark, right, for a spark to be produced, it has to ionize air. So if there's less air, there's less it needs to ionize. And as the lower the atmosphere gets, it gets easier and easier to spark until we get this lurid amount of plasma in there. Right? So now, that guy's quiet. Right, do you guys hear the bell?
The battery died.
Now what's
Bell.
Oh, the microphone's now picking this up. Awesome. So, with this going, can you hear the bell? Now, before you answer that, notice that there are two different sounds. There's the bell, and then there is a thing that is shaking that is attached to a metal lid, right? Which is not in the vacuum. So the bell is a high tingy sound, and then there might be a low thud of a thing shaking. So can you hear the bell? Not really, right? Now, just to prove this, we can also run the whole experiment in reverse, because we're good scientists like that. So listen for the bell as I let the air back in. As the air returns, it suddenly has a medium to get that vibration to you again, and we can hear the bell. So here we've been looking at light and sound, right? Both as forms of waves. Now sound we're a little bit more intuitive with because we have a lot of practice with it. So we're going to put sound aside for just a moment and do a little bit more about light and electromagnetic waves. Bring in the next charts here. So, we all kind of know sound. You shake a thing, it makes sound. How do you make electromagnetic waves is a much harder question, because that's not a thing that we're really used to doing in our day-to-day lives. So if I said to you guys, pardon me for not exactly knowing how much schooling you all have. If I said to you guys electric field and magnetic field, do you know what I'm talking about? All right. So electromagnetic waves are literally waves in electric fields and magnetic fields, right? And they happen to go together quite nicely as shown here. So we can do this as one wave, and the electric field is vibrating, and the magnetic field is vibrating. And that's how it's going through reality, right? As this. Now, how can we produce an electromagnetic wave, right? Well, let's go backward. If we wanted to change the electric field in a space, how could we do that? A lot of really timid answers. One brave person to yell something out and we can go from there. Right? Not air, because we're dealing with electric fields. Right? So what produces an electric field? An electric charge of some kind. Right? Electricity is an electric charge moving. Right? So we need some kind of electric charge. So if I had an electric charge here, right, and say I can run it up and down the steps in a building. So I can hold it in any window along those stairs, right? And then my friend who's across the street, also in a staircase, right, is going to always try to be even with me in the stairs, right? Ideally, we'd like to hang out next to each other, but we can't. We're stuck in the stairwells. So as I run down the stairs, as soon as he notices I'm running down the stairs, he's going to run down the stairs too, right? And as I go down, he goes down. As I go up, he goes up. Now, it should be noted that there will be a slight delay in this happening. He has to notice that I'm leaving before he's going to run. So we can do that here. So this guy,
and a real quick point. This is a grandfathered transmitter. These are not available in stores and have not been since 1926. This is one of the cool things about working at a fossil institution. Okay? This is an 85 megahertz transmitter, transmits at 30 watts. If you touch it, you get a radio frequency burn. But today, you need a license. This is a broadcast frequency. But in 1926, there was no FCC, there were no rules, and you could just have a transmitter. Okay, so this is a 30-watt FM transmitter. It will bugger your radio if you're listening right now, but Pete's going to show you what we can do with 30 watts of radio. Okay?
So, as we turn this on, we now have, these are lighting up. You don't need to worry about the light. That's just the vacuum tubes heating up so much that they're effectively becoming light bulbs. Now also, you have to kind of believe me that we are now shaking electrons in this antenna, right? So if I move an electron this way, it's going to push all of the electrons to its left, further to its left, right, until we get to an end. And if it moves to the right, it's going to push all the electrons further to its right that way. So we can imagine that there's some amount of charge that's moving back and forth along this line, right? Now, if we could get another source of charge that would want to follow that charge around, we might be able to notice that. And we can do that by having a light bulb on another antenna. So if I bring this antenna here, the demonstration is broken. The light bulb is not lighting up.
Oh,
We're wasting a
no!
bunch of time. So we have a problem here.
There we go.
So what just happened? What did I change? I changed the direction, right? So we said before, right, if we go back to the stairs analogy, if I ran down the flight of stairs, my friend would run down the flight of stairs, right? What if he's in a one-story building and I run up the flight of stairs? Can he follow me? No. He's stuck on that floor. But if I was then also on a one-story building and started to run along the hallway, he could chase me along the hallway, right? So the orientation of the antennas is also vitally important, right? When we get to the world of things like cars, right, when you're picking up radio waves, we can actually get to just, you guys have noticed on probably slightly older cars that didn't have XM radio, how there's like a wire grid that's going along like the back window or a side window or something that's kind of etching all the way across. That's an antenna, because they don't know how you're going to be facing relative to the antenna that's broadcasting. So they just have 7 of these in an array as much as possible, and one of them will probably pick it up.
And of course, what Pete's got here is called a dipole antenna. It is virtually identical, right? You know, your grandparents had these things, right? Okay, so this was when you used to pick up, and this is a dipole antenna, and we've got electrons sloshing back and forth there, and in doing so, they run through this light bulb. With your antenna, they slosh back and forth and go through your TV set, and that's how you used to get channel 6, okay? But of course, that's contingent on obviously tilt and things, and if you have a cable line, then your signal is not dependent on tilts, and you don't have annoyed grandparents pushing rabbit ears all over the place.
And the wire hangers.
And the wire, yes. All right. So Pete has covered some fairly decent theory. Can we trust him?
Probably.
He talks a good line, but you know, let's get some real scientific equipment here. That's right. Once again, grandfathered in. These are as hard to buy as that transmitter. And it's killing me because these are wonderful. Because it turns out physics teachers are about as coordinated as 3-year-olds. And so you really want slow 1-speed cars. Otherwise they crash them off tables and mess everything up. So what we've got here are 2, count them, 2 Fisher-Price cars, but they both have the same frequency. And so I don't even need to have good coordination to do that. Wow! Isn't he amazing? Because when I send a signal out from this, both these guys get a radio signal, okay? And what's happening, of course, is what Pete described. We've got electrons running up and down here, and those electrons are then, you know, coaxing these guys to do the same thing, and when they do that, the car moves. Okay, and if we get them to run the other way, all right, the car knows to go the other way. And all of that's peachy, unless we put another antenna that's really, really, notice this antenna doesn't bother this guy because it's really skinny. It grabs a little of the energy, but doesn't really shadow this guy. What if we've got a piece of screen? Okay, so now these guys are right here. They're ready to go. Okay? And so now I'm going to send this electric field in here. These guys are going to bounce around. He's going to start moving, but then the field hits this wire mesh. And it now uses its energy to move electrons in the screen, which means there's no energy left on the outside of the screen. Okay? And so what comes of all of this? I hope this works. So this guy lost the signal. Am I whistling Dixie? Did his batteries just run down? If I send the signal down through here, then of course he still gets it. Okay? And what we've got here is called shielding. Sometimes we refer to this as a Faraday cage. Okay? It's one of the reasons we have a terrible time getting radio reception in this building, because the building has a lot of reinforcement bar in it. So although it looks like a masonry building, hiding inside is a lot of steel mesh. This essentially is a coaxial cable. I don't know whether you've ever taken a look at a coaxial cable, but a cable TV connection has something on the end. It's a round wire. If you strip that wire down, you discover that there is a sheath. Coaxial means it's sharing an axis. And so there's a woven sheath of wire that forms a tube, lo and behold. Okay? And then a center wire that goes through a plastic sleeve. So they don't touch, but instead of being side by side, one's inside the other. And the upshot is that the outside one becomes a shield. Why do I want a shield? Because if I put a signal in the end, it runs down the wire. But if lightning happens out here, that's a radio signal I don't want. And it gets blocked by the shield, just like my signal to the car, which means I don't get disturbances or static on my electronic medium. Okay? And it also works for audio cables and anything else. Anytime I want to run a signal into an amplifier, so it's a weak signal that's going to go in and get enlarged, I do not want to pick up noise on it, and so I use shielded cable for that signal. Okay? So we end up with a very visible application of what sounded like some pretty highfalutin theory there. Okay? And it works just fine, and it's really at the heart of the electronics industry. Okay, are we done with this?
So this has been light again, all right? Electromagnetic waves, light. So now we can go back to sound, all right? So if we wanted to look at sound and how it changes the medium, we would need something like, I guess we'd call it an interferometer.
Yeah, you know what? I
Oh,
think
we're going straight to this
think
one?
right, because you guys are probably looking at a bus at 11:30, right?
When are you guys
Right, is
leaving? Now?
How are you doing time-wise?
11:45 for them?
We'll just stay here.
11:30? That's fun.
Can we get 10 more minutes?
Yeah.
Okay,
All right.
so we can do this. We don't want you to miss this part, but it's nice to get the development.
So this is an acoustic interferometer, right? You can also think of it as a super goofy trombone. So here at the front we have a function generator. So here we have a function generator. And that function generator is driving a speaker, which is right here. Now, as we've said, the sound is being produced by a diaphragm that's moving back and forth, which is then pushing the air. Once the air gets pushed here, it has two directions it can go. Along the blue side or along the white side. Eventually, both of them will leave out through this hole, and then you hear it. Now, if we change these tubes a bit, sound changing?
Now, why?
I'm not running the mic yet.
But we should be running the signal.
Yes, you are. It's on the screen.
But, oh, okay, gotcha. Thank you, sir.
So, we can hear that change, right? But to make it a little easier, we've taken another speaker and we've wired it backwards, which makes it a microphone. And we can jam that there. So now, instead of just hearing that difference in volume, we can see it. So, why is that happening? It should be an easy question. We've already talked about it. No, right? So, first let's do this one. The sound is not going away. I haven't touched the speaker volume. But now we have almost no signal coming out. Almost silent. How can two noises combine to be silent?
Cancel each other.
Just yell, it's fine. Right, they cancel out, right?
And real quick point. We're asking you to believe it's silent, but you're saying, but there's noise, right? But the problem is, you're hearing this, right? This guy's still making noise. We're listening here. And if we could get each of you to put your ear in here, there's no noise up here. But regrettably, you're far enough away that you're getting samples of both, okay? So that's why you hear noise but don't see noise, okay?
Now, if we change the path length, so now one of the waves has further to go. So both of them are moving at the same speed through air, but now by changing the paths, we've gotten a combination where they meet, we happen to get a +2 and a +2 at the same time to get a +4, instead of a +2 and a -2 where they would cancel out, right? As we go through, so this is the same as if you've ever heard an orchestra tuning up, how they're all trying to hit that same note, but there's this warble as they're getting into tune, and that warble slowly gets slower and slower, and the orchestra also gets louder and louder, right? That's one of the big reasons we always want to be in tune as a performer, because you get this much increase in volume without any additional effort, right? Just because you're in tune, your band is that much louder. Now, we've been saying that these are compression waves, right? That we have this gas that's under high pressure and low pressure. If we did something like put tire gauges all the way along the top of this, right? We could see the high pressure and low pressure as it moves, right? But you guys really wouldn't be able to see the tire gauges, and tire gauges tend to react kind of slowly and are kind of boring. So instead, we could poke holes in it, right? And then the pressure would come out more at the high pressure than at the low pressure. But it's kind of hard to see gas because most gases are pretty transparent. But if the gas happened to be on fire, then we would be able to see, well, what kind of a lunatic would fill a tube with flammable gas?
You guys are I am cold.
So, part of this guy is a little bit slow to light up because we haven't been playing with it. So he needs to fill with propane here.
screams coming out of it.
So we're being a little cautious today. We don't want this to disassemble itself before the next show.
Right, see? Right, it's not that we care about your lives, it's that we have another show to do.
Sorry, so this guy's, yeah. So this is called a Rubens Tube, named for its inventor, Mr. Rubens, not the sandwich. Now what's great about this guy is that it allows us to see these sound waves in a different way than just the oscilloscope. So if I put our sound system through the oscilloscope here, right, we can see the waves that are going in. And if I change the note here, you'll find that there are certain notes that seem to like it a bit more.
Yeah, we're getting good one. Because in the long run, this is one pipe from a pipe organ. So it wants to play a specific note or harmonics of that note, and the other notes it doesn't much react to. And if we get, you can kind of see highs and lows. So we've actually got an idea of what the difference between two high points is going to be half a wavelength.
Now, if I was as musically inclined as Bill sometimes thinks I am, I could play you something cool. You could see standing wave patterns in it. That would be great. Unfortunately, I am the less musical gifted of my brother and I, which is why I teach for a living, and he's a rock star out in LA. But instead, we have another artist that can show off just how good this is.
This is either going to be Mike or the Minion, right?
Yeah. So, in addition to just the fact that Adele is nice to listen to, one of the things that you can really see here, which makes her stand out as a musician, part of the reason we like listening to her, is that she can sing an almost perfect sine wave, right? Which our ears have been brought up to think sounds pretty. So, as we play this through, every once in a while you'll see her hit a note that is such a perfect sustaining sine wave that you can see it along the Rubens Tube. Now believe me, we've played a lot of music through this, trying to figure this out, what looks good. And it turns out, the only two things we have found that looks good in a Rubens Tube is Adele and a bassoon. And that's it. Nothing else sounds good enough to produce a decent Rubens Tube. But especially here, you can really see these standing waves that she can produce.
And I have to point out, you'll notice this is just vocals. Okay, Pete realized he could go online and find places where they pulled the music out and just have the vocals, because the kick drums in almost all pop music just create big poofs, and the big poofs hide most of the waves that you're trying to look at. So this was really a biggie. If you get involved in trying to create one of these things, step one is to get the kick drums out of the picture.
That being said, we'd be scientists if we didn't show you what kick drums look like. So you can see here there are some sustained waves in it, but mostly you can hear a drum set. So, on this note of fire and Katrina on the waves, we'd like to thank you for spending your morning hanging out with us, looking at our physics cards.
Very much. Hope to see you next year.